Okay, I just want to take a brief minute and talk, summarize what we finished last Thursday and show an improved file that can help illustrate what we've done. So first, we're starting here with a series, this geometric. Its common ratio is x, and so converges on this interval, which basically means that if I take these infinite number of terms, it will equal this as long as I choose a value of x that's in between there. And we saw that a little bit with GeoGebra and how it fits the curve from -1 to 1, but not outside of that. So here, we're talking about how we can use that power series, use this information here to generate new ones that may have different intervals of convergence. And part of this is about thinking about the center and changing where the center is and a visualization of that. So first observation is that I can think of 1 over 5 minus x as 1 over 1 minus the quantity x minus 4. So if I distribute this negative, I get exactly this statement. So really then by substitution, I should be able to write this side over here, because basically every x has become an x minus 4. So that means that this is equal to 1 plus x minus 4 plus x minus 4 squared plus et cetera, et cetera, et cetera. And this is a geometric where the common ratio is x minus 4. And so that also then means that when we're thinking about our interval of convergence, that x minus 4 should be between 1 and -1. So this should converge when x is between -3 and, how about 3 and 5. We're going to add 4 to this. So, but that's not the only way it could be written. So notice that this is actually moving the center, again, is the language that we use, that this would be centered at 4. Now, it's not surprising that looking at this interval of convergence, that the center is at 4. So it really should be centered about that, and here's why. When you look at this x minus 4, it's this center from -1 to 1, so if I rearrange it, then 4 is the center. So 4 is the center, there's the interval of convergence. So what if, though, we write it differently? Now, here, I'm just looking at this and going, well, I could take a 5 out. So this is then 1/5 times 1 over 1 minus 1/5 x. And again, if I multiply that 5 back through, I'm back to this same statement. So whatever I'm writing here is equivalent, at least on some interval. So, okay, so this one, if I'm looking just here at the highlighted portion, if I could think substitution. Notice though this one appears to be centered at 0. So let's do that. Let's write out what this then is saying with this substitution of -1/5 taking the role of x. So we still have this 1/5 out in front, and so times. So 1 plus x, x being -1/5, positive 1/5, x, so all of that's taking the role of x, and that then is actually r, so I should have a plus 1/5 x squared plus et cetera, et cetera, et cetera. Now, we're following the same pattern, which means we should be really matching the same function, but this one is centered at 0. So if we think about the interval of convergence for this, like the common ratio here is 1/5 x, so it is the thing that should be between -1 and 1, which means x should be between multiplying by 5, 5 and negative 5. So notice that this interval of convergence is larger, has a larger radius. The radius here is 5, the radius here is 1. This one is centered at 0, this one is centered at 4. So let's look at this geometrically. So I have here our function 1 over 5 minus x, which is equal to that infinite series being written in two different ways. So I have here in purple the one centered at 4. So notice that right now I'm just constructing this first term, which is just showing a horizontal line here. The brown one is the one centered at 0. So let me add a term in here. So this one is 1 plus x minus 4. So yeah, it's not simplifying that, but that's 1 plus x minus 4. This is our 1/5 that's out in front, and plus our 1/5 x. Let's look at the difference already. So here's the function that we're fitting. Now, obviously, the one that's centered at 4 is doing really well around 4. In other words, this function could be a good approximation for this function if I want a value near 4. If I want to think about 4.1, I want to think about what 4.1 would be in this function versus this function, like locally linear, all those conversations, that this purple is a much better approximation near 4 than this brown. And as this increases, that's really what we should see. We should see that the purple one is fitting near 4 on its interval of convergence, and the brown one here should be centered here about 0, and we should notice its interval of convergence as well. Let me see if I can illustrate that well. It's going to be easier to see on this side, but let's increase it. If you look over here at the brown one, do you see that it starts deviating a lot? I can see the dashed line like really obviously here at 5.5. And if I think about the polynomial, like this is an x to the 6th, so it's got to have an in behavior that's eventually pointed up over here. It's just way off the screen. So I know it can't be fitting this thing that has, when you think about this horizontal asymptote that this thing has at 0. But if I look at the brown one, again, it's fitting pretty well in here now, but the purple one is still better near 4. And again, it's just where it's centered. But do you notice that the purple one isn't fitting as much of the curve? And that's, again, that radius of convergence is less. So as I continue to add these on, so this is through 20, and you can see, again, like eventually we think that the brown one, right, it should be fitting better near 5 than it is. We would just need more terms. But notice that if I really wanted an approximation for this function for some reason at 5, that the purple one's going to do much better, right? Like I shouldn't be approximating 5 because that's the asymptote, but let's say 4.9. So 4.9, like, yes, we should probably be looking at the purple function versus this one, especially if I only have 20 terms. Now, ideally, if we could think about keep going before I lock up my computer, then it would fit better and better and better. So I hope that helps a little bit of visualization. We can see the purple centered at 4, and it's pretty obvious here at this point, the centered at 0 for the brown one. So, but they definitely are agreeing in here. So that's what we have here. We have two different representations of this that are thought of in different ways, one of them by moving the center, one of them by manipulating it, by factoring out that 5. Both of them are representation of this function, this function. Um, it's just that it's going to be different intervals where that function is matching it. So I hope that helps a little bit of seeing the interval of convergence.